So you may have been wondering why there was this picture of I don't know, some police officer, highway patrolman, or whatever. That's obviously kind of blurred out right there, but that's a radar gun. What the heck is going on? Why is this picture here? So we're going to see. By the end of this lesson, we'll see what the connection is. Being able to understand and apply the mean value theorem and Rolle's theorem. First up, Rolle's theorem. So let's write this thing down. Formally, Rolle's theorem says, let f be continuous on the closed interval from a to b and differentiable on the open interval from A to B. Okay, two key conditions that have to be met before you can even start to apply Rolle's theorem. It's got to be continuous on a closed interval and differentiable on the open interval. So make sure that if you're required to apply this theorem for a particular question, maybe it's on a free response question, that you point out those conditions are met. Okay, but there's another one. If f of a is equal to f of b, remember that the y values have to be the same, then there exists at least one number in the interval from a to b such that f prime of c is equal to 0. So the way we were able to demonstrate this is that we took ourselves a straight edge and we connected those 2 points, made a horizontal tangent line. No, it didn't. Made a horizontal secant line. And then if we scooched it up along our function, we were able to see that we would have a slope of 0 someplace on our original graph. And that's exactly what Rolle's theorem is guaranteeing is going to happen as long as our function's continuous and differentiable and our y values are the same. All right. Oh, if you take a look over here, Michel Rolle is speaking to us. He says, I totally hate calculus. That's exactly what his voice sounds like, by the way, or sounded like a couple hundred years ago. So the story goes is that he was not an advocate for calculus as it was coming out. He was a critic, said it was all fake math. And yet here we are a couple hundred years later, and he's in every single calculus book for sure. All right. So Rolle's theorem, basically saying there must be at least one horizontal tangent line in our interval. Again, what are our conditions here? Let's look at a couple more pictures, and then I'm going to write down each one of these conditions so we can really hammer them home. Okay, so here we've got ourselves a horizontal line. Horizontal line is continuous and differentiable on this closed interval from A to B here, definitely. And if I pick basically any point in there, its slope is going to be 0 in between those 2 points. Why is that? Because the slope's 0 everywhere on that. Okay, so that's a silly case. All right, so here's another one. These two y values are the same on this continuous and differentiable function, and then you can see right here at C, we have a horizontal tangent line. The slope is 0 there. Okay, and then over here on graph C, we have a continuous and differentiable function. And notice that on this one, again, the y values are the same. If I connect those two, it'd make a horizontal secant line, and then we have 2 points, 2 tangent lines with a slope of 0. And then last one here, something that looks parabolic. Our two y values are the same. We have a little turning point in between there with a horizontal tangent line. Okay, so then let me come over here and a couple of things. Let's make sure that where the heck is my Apple Pencil? Oh, it's in my pouch. I have a pouch because I'm a kangaroo. If I draw in a function, first of all, that violates one of the conditions, the whole idea of it being differentiable. And I'm going to use the absolute value this time. So if I use an absolute value graph, bam. And here are my two y values. My two y values, A and B. Those two suckers have the same y value. And if I were to connect these two for my, oh, that was absolutely perfect. Look how nice and horizontal that is. Okay, try that again. All right, so there is my horizontal secant line. If I were to pick this thing up, I can see that I am not guaranteed, pick it up, come on, there we go. I'm not guaranteed a slope of 0, a horizontal tangent line on this graph, right? And I absolutely exclude this turning point here, or this sharp turn, I should say, because there's no slope there. Yeah. All right, so I know that I need to have both of those conditions being satisfied before I can apply Rolle's theorem. So Rolle's theorem goes like this. If there are 3 conditions that have to be made, are met, I should say. So the first one is that it has to be continuous on this closed interval from A to B. The second one is that it has to be differentiable on the open interval from A to B. And this is going to be very, very common on a lot of these theorems, that the continuity occurs on a closed interval and the differentiability occurs on open intervals. And then finally, there's one more for this one more condition, and that's f of A, that's the y value, has to be equal to f of B, the other y value, at the endpoints, right? Those three things have to be true. If those three things are true, then there is a C value in the interval, the open interval from A to B. In other words, it doesn't occur at the endpoints, such that, that's a pretty that, f prime of C is equal to 0. So anytime you see on one of those multiple choice questions where it says something about the derivative equaling 0 and you're trying to find a value where that's happening, it's definitely concerning Rolle's theorem, Rolle's. And you want to make sure that you apply those three conditions. And you sometimes can get one of them for free because sometimes they only say it's differentiable. But if it's differentiable, then you're going to get that continuity part for free, because remember, differentiability implies continuity, but not the other way around. All right, so let's try to apply this on example 1. To find the x-intercepts of f of x is equal to, we got ourselves a polynomial. It's like an algebra 1 question here. And show that f prime of x is equal to 0 at some point between the two x-intercepts. Okay, let's do it. So first of all, talking about our conditions, this is a polynomial. And polynomials, let me see if I can spell this correctly. Polynomial, there we go. I couldn't spell and talk at the same time. Polynomials are continuous and differentiable everywhere. So they must be continuous and differentiable on whatever interval it is that we're going to set up. And that interval is going to be determined by the two x-intercepts that we're supposed to find. So let's find those things. So to find x-intercepts, there's no derivatives involved here. Instead, I just set the thing equal to 0. X-intercept. So 0 is equal to x squared minus 3x plus 2. I'm going to have to factor this. Hopefully we can handle this. I know that's an x, that's an x. Got to multiply up to 2, add up to negative 3, negative 2, negative 1. I'm pretty sure. Okay, and then my x-intercepts then must be a positive 2 and a positive 1, which means our closed interval must be 1 to 2. Okay, so let's make sure that our conditions are met, right? So since f of x is a polynomial function, it is continuous and differentiable. I'm proud of myself for spelling that correctly. Everywhere. So it must be continuous. Wait, we have to remember, say that it's continuous on that closed interval. It must be continuous on the closed interval from 1 to 2 and diff, I'm just going to abbreviate it this time because I don't trust myself, on the open interval from 1 to 2. Okay. And then there's one other part, right? The other part is the y values have to be the same. And I know my y value is the same because we found that there were zeros. The y value is 0 at both of these x values. Okay. Since f of 1 is equal to f of 2, which is equal to 0, then there exists a value of c in the open interval from 1 to 2 such that f prime of that c value's got to equal 0, right? So in between those two y values, I mean, if I were to draw myself a graph of this thing, in my two x-intercepts, wherever those things are, of course, it makes a horizontal secant line. Someplace in between there should be a tangent line that has that same exact slope of 0, right? It's going to be the turning point, basically, for that parabola. So let's find that thing. Now, let me just point this out. This is Rolle's theorem that we just applied here, and Rolle's theorem just tells us that it happens. It doesn't tell us where it happens. We have to do some algebra, some calculus, or whatever in order to find the thing, and that's what we're going to do next. So in order to find it, I need to actually take the derivative. So what the heck was the function again? I think it was x cubed, no, it wasn't a cubic function, x squared minus 3x plus 2. Take its derivative. F prime of x is equal to 2x minus 3. And then we said that the derivative has got to be equal to 0 someplace in that interval. So just set that thing equal to 0. 2x minus 3, add the 3 over. Divide by 2. X is equal to 3 halves, otherwise known as 1.5. And guess what? 1.5 lives in that interval. Even though the guy hated calculus, he apparently knew what he was doing.